The question of how big the universe is seems simple, but the answer is surprisingly layered. First, we have to distinguish between the entire universe and the observable universe. The observable universe is everything we can possibly see from Earth, and it has a very specific, measurable size. The size of the entire universe, on the other hand, is something we genuinely do not know. A common first guess is to take the age of the universe, about 13.8 billion years, and assume the observable part is a sphere with a radius of 13.8 billion light-years. It makes intuitive sense, since that's the maximum distance light could have traveled to reach us. But this calculation misses a crucial piece of the puzzle. It forgets that the universe itself has been expanding the entire time that light was on its journey. The space between us and a distant galaxy has stretched, almost like a rubber band being pulled. So the galaxy that emitted light nearly 13.8 billion years ago was much closer to us back then. While its light traveled, that galaxy was carried much farther away by the expansion of space. When we do the full calculation using our best models of cosmic expansion, we find that same galaxy is now about 46.5 billion light-years away from us. This gives us a radius of 46.5 billion light-years for the observable universe, making its total diameter a staggering 93 billion light-years. That's the boundary of our cosmic horizon, the sphere of everything whose light has had time to reach us. Just a century ago, this concept would have been unthinkable. Before Edwin Hubble's work in the 1920s, most astronomers believed our own Milky Way galaxy was the entirety of the universe. His discovery that distant smudges of light were actually entire other galaxies pushed the walls of the cosmos out to an almost unimaginable degree. If we try to look to the very edge of this observable sphere, we don't see a wall or an endpoint. What we see is the cosmic microwave background radiation, or CMB. This is the oldest light in the universe, a faint afterglow from the Big Bang. It was emitted when the universe was only about 380,000 years old, a time when it cooled enough for atoms to form and for light to travel freely for the first time. This surface of last scattering is in every direction we look, essentially forming the glowing inner wall of our observable bubble. This naturally leads to the next question: what lies beyond that horizon? While we can't see it directly, our best assumption is that it's simply more of the same. The cosmological principle, a foundational idea in modern cosmology, states that on the largest scales, the universe is basically uniform. It suggests there's nothing special about our location. Therefore, an observer in a galaxy 100 billion light-years away would see their own observable universe, filled with galaxies, just like we do. This then raises the ultimate question of whether the entire universe is finite or infinite. Current evidence points towards it being infinite. By studying the geometry of the universe using the CMB, scientists have found it to be almost perfectly flat. In this context, flat doesn't mean two-dimensional. It means that parallel lines stay parallel forever, and the angles of a triangle add up to 180 degrees, just like on a flat sheet of paper. According to general relativity, a flat universe is an infinite one, stretching on forever in all directions. It's also possible the universe is finite but unbounded,
like the three-dimensional surface of a four-dimensional sphere.
In that scenario, if you could travel in a straight line for long enough, you would eventually end up right back where you started, without ever hitting a boundary. However, the data we have strongly suggests the simpler, flat, infinite model is the most likely. The edge of our universe isn't a physical boundary, but a temporal one.
It's an edge in time.
And this edge is dynamic. The expansion of the universe isn't just happening, it's accelerating, driven by a mysterious force we call dark energy. This acceleration has a strange consequence for our future view. Galaxies that are very distant are being carried away from us by the expansion of space faster than the speed of light. This doesn't violate relativity because it's space itself that's stretching. Over immense timescales, these galaxies will cross a cosmic event horizon, and any light they emit after that point will never be able to reach us. So, in a very real sense, the edge is fading. As the eons pass, fewer and fewer galaxies will be visible to our distant descendants. The observable universe, in terms of the number of galaxies we can ever hope to see, is actually shrinking. We live in a special time when we can see this vast 93 billion light-year wide tapestry of cosmic history. But it's a view that is slowly, inexorably dimming over the horizon of time.